Okay, let us start. Let us wait 1 or 2 minutes, then I will start. Okay.
Sir,
Yes.
sir, could you please explain that poison kernel
Huh.
part once again?
Yes, yes. I will do that. Okay. So let us start then. Okay. Yeah. So we are doing the Laplace equation, and we're in the final stage of the of this chapter, and then finally we will do the parabolic some heat equation. And this is very similar to the Laplace. Of course, there are some new things are also there, but today we will finish this Laplace equation. So let us just tell you what is let us recall. So we are doing the Green's function, right? Green's function. Sorry. So what is that? Our aim is to solve the following PD, where minus Laplacian of u equal to f in omega and u equal to g on the boundary data. The boundary data is given to be u equal to g on del omega. Of course, where omega is a smooth bounded domain. Okay, where omega is a smooth bounded domain. It's a smooth bounded domain. You know what is the meaning of a smooth bounded domain. So, so we see that if u is a solution, is a solution to the above problem, let's say star or p. If u is a solution to star, then ux will be given by it as a representation omega fy g of xy minus del omega gy del g by del nu, the boundary. And what is g? This g is known as the Green's function. Okay, and it is explicitly written. It is explicitly written as g of xy is just translate of the phi of y minus x, and there is some harmonic function phi superscript y for each x. Okay, and this and that is xy in omega with, of course, x not equal to y. So at the diagonal x equal to y, this Green's function is not defined. Okay, otherwise it is defined. This is a, so the definition gx is defined omega minus this set. So this is a domain. This is a domain of G. Omega cross omega minus set minus is the x comma x. It is not defined on the diagonal set. Okay, because you know there is a, and what is phi x? This is you know. This is you know explicitly what is phi. Phi is the fundamental solution. Fundamental solution. Okay, and this is the harmonic part. Harmonic function. This is a harmonic function satisfies some boundary condition, that is Laplace p of xy equal to 0 in omega. This is a harmonic function which satisfies some boundary condition. What is that? Phi of xy is p of the boundary set in del omega. Okay, so this is the thing. So you can explicitly find what is the Green function G. Okay, is that clear? All of you, is that clear?
Yes, sir.
Okay, so this is a definition of a Green function. So then we done some properties of Green's function. Properties of Green's function. Can you just recall some of them? That Laplacian of y, g of xy is 0 for all y in omega with x not equal to y. Okay, and g of xy is equal to g of Okay, it is symmetric for all x, y in omega with x not equal to y. Okay, clear? So we have done this, all those things. Okay. Next, then we have computed some example, explicit example. What is the, so we want to compute the, so as you see, if we know the Green's function, then your life is easy to solve that problem. Okay. So the example we cook up is, first example was the upper half space. Upper half space. That is x1, x2, dot 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 up to xn minus 1, comma xn belongs to Rn with xn positive. This is Rn plus. Okay. So main, because we know that the Green's function is given with that there are two entity, right? One is phi of y minus x minus phi of xy. So to find the Green's function, it is enough to find, because you know explicitly what is this. Want to find the harmonic function. Okay. We wish to find, we want to find the, find a harmonic and harmonic function. And I said and, so it may not be x unique, right? Harmonic function. What is this? Laplacian phi x equal to 0, and it should satisfy the boundary condition when yn equal to 0, and this is when y is equal to the whole space Rn plus. Okay, we want to find this harmonic function. Okay, so what I told you, right? So the problem, so which is the closest harmonic function? This is the closest harmonic function. This is a harmonic function except this is harmonic minus Laplacian of phi is harmonic except possibly at one point. What is that point? Y equal to y not equal to x. At y equal to x, you don't know. Of course, this is not right. There is a singularity. Otherwise, phi is a very nice harmonic function, right? If you consider the domain omega minus x, y not equal to x, minus y equal to x. If you consider this set, in that set, this phi fundamental solution is a very nice harmonic function. So we have to find this harmonic function, we will try to get a help from this fundamental solution. So we want to find a function such that it is satisfied and also satisfy the boundary condition. Okay. So for that we define phi x to be phi of y minus x bar. What is x bar? It's a reflection with respect, and this x bar, y is never equal to x bar in when y is in the upper half space, because x bar is some point which is here x bar, here this is xn equal to 0, this plane xn equal to 0, this is x. So I take the reflection with respect to this plane. You understand? I took the reflection with respect to this plane xn equal to 0, and you see that phi of y minus x, so y is never equal to x for y in Rn plus 1, because this x bar is not in Rn plus, right? Not, so this phi is a, if you take the Laplacian, you can take it has to be 0, right? Because y is never equal to x bar. So it's a very nice harmonic function, and because I have taken the reflection, the distance between any 2 points from this point to the x and this point to this point is same, and that is why we can conclude that it will also satisfy the boundary condition. That is when y is equal to the plane, y is in the plane xn equal to 0. Okay, so this is our example. Now, as Atharva mentioned that we want to study what is a Poincare kernel, right? Poincare kernel is nothing but we want to solve this problem. Minus Laplacian of u equal to 0 and u equal to g. We want to solve it. This is in Rn plus, this is in del Rn plus. So instead of f, you take a particular problem, Laplacian of u equal to 0 in Rn plus and u equal to g on the del omega. So just forget it. Suppose you have a solution, u is a solution. Then how u looks like? You know that. This is omega. This is your f, y, g of xy, dy minus del omega g of y del g by del nu at the point xy d sigma y. You know that if you use a solution instead of 0, if it is f, then this is the solution. So if f equal to 0, so what will what will happen to the first term, this term? Hello?
0 it will.
0, because f equal to 0. So now you are the equation boils down to omega g is the function gy del g by del nu, because this g is given, right? This is the answer, yes or no?
Yes, sir.
Okay. Now we want to explicitly we can compute whether in case when omega is Rn del Rn. Sorry, Rn plus, that is minus del Rn plus gy del g dou g by dou nu at the point xy d sigma y. We want to compute explicitly what is del g by del d. Okay, and we will see what at the point when omega is in Rn. Okay, so what is that? We have compute, you can directly compute, right? Del g by del yn, any point in xy, you can compute the yn derivative is as minus 1 by n alpha n y minus x. I am computing for n greater than equal to 3. Okay, because you know what is n greater than equal to 3, phi of xy. That is the fundamental solution. What is that? Fundamental solution is some constant Cn. You know what is that constant? Constant x minus y. Okay, for n greater than equal to 3. Okay, we just use this fact. Okay, by y minus x whole to the power n minus yn plus xn by y minus x bar whole to the power n. Okay, now you want to compute del g by del yn when y is in del Rn. That means you have to compute here your xn is equal to yn is equal to 0. You just compute it. If you compute, you will end up the result will end up with xn by n alpha n alpha n. So you just compute, you will see. Okay, there is nothing, you just compute. So xn 1 whole square n by 2. Okay, these we call as a this minus of del g by del yn is the Poisson kernel. And y is in clear. That means these I can write, this ux I can write in the following way. I can write as I can write in this way, that if you use a solution to the equation n alpha n, this is r del Rn plus Rn minus 1 gy by xn square d sigma 1. It is written as, sometimes it is written as Rn minus 1 kxy gy d sigma 1. Okay, and this k is known as Poisson kernel. Is that clear? Is that clear?
Yes.
All of you. Now I was expecting a question. No one has asked this question. So I said that when u is a solution, when u is a solution to that PDE, then you can write u in terms of this. Is the converse true? Is the converse true? The question is clear. Is the converse true? Yes or no? Is the converse true? So as I say that when U is a solution, you will have a representation. Now I am asking a converse question. Suppose I define a function u of x such that like this, del of Rn plus the Poisson kernel gy d sigma y. Then whether minus Laplacian of u equal to 0 and u equal to g on del Rn. Is that true? Is that true? Yes or no? Yes.
Yes, sir.
This is also true. You have to, this I give you an exercise. Check. Okay, this is there in the book of Evans. Okay, just check that if ux is given by this equation, then it is also a solution. Is that clear? Is that clear? All of you? It's not difficult. You just try to do that. Okay. Okay. Now another example. As I said in the last class, we'll do another example. Green's function for the unit ball. The ball I denote B is x in Rn sorry, ठीक है? Green's function for the unit ball. B equal to S, you have to find the Green's function for ball. So we need the harmonic function phi x satisfying phi of x y and y in the del B. Okay, that means your domain omega is nothing but this one. What you will do? What you will do?
We'll invert the singularity, like reflect it
Ha
across the boundary of the ball.
ha. So let x belongs to B. Okay, define x tilde as x by mod x. This is called inversion. Perhaps you know this in complex analysis. So where this x tilde point lies? So x is inside the ball. So where will be this x tilde? Any idea?
Outside.
Why? You just take the modulus. Then it will be 1 by mod x. So as x is in B, 1 by mod x is greater than 1. That means x tilde will be like somewhere here. So you are outside. X tilde is a point which is outside the ball. And why? Just a minute. Just a minute. Okay. Greater than 1. So you are out. So x tilde is an inversion. Okay. Okay. So this x tilde is called the inversion with respect to unit sphere. Okay. Of course, it has some property. Let's see. Okay. So now define your phi xy, the harmonic function, as phi of mod x y minus x tilde. Okay. So you can ask me why I have defined like this. So is that a harmonic function? Because why? Because only problem is this is a function which is a harmonic function. Where is the only, so as a function of y, as a function of y, where is the problem? Hmm? This is a fundamental solution. So where is the problem of this function?
So at y equal to x tilde, but it will
Y equal
never
to
be
x
equal to
tilde.
x tilde.
Exactly. So Laplacian of y phi of x y minus x tilde is always equal to 0 except y equal to x tilde. But this is 0. This x tilde is now outside the ball, B complement. So this is always 0 for all y in B. Yes? Is that clear? So this is right. If I define in this way, then phi xy Laplacian of y is equal to 0 for all y in, because the singularity of this function is only at y equal to x tilde, but the point x tilde is now outside our domain. Okay, because outside x tilde is big. Now you see that. So now we have to compute the this at the del. If suppose we have y is in the boundary, then what is the distance? Suppose now y is in del b. Okay, then what is the distance between, what is the, so y is in del b means mod y is equal to 1. Now we have to compute the distance between these 2 points, right? Yes or no? Now we claim that phi of xy is equal to phi of yx if y is in del b. If y is in del b, yes, this we have to prove, right? That means that is, I have defined, you know what is the way I have defined. Is that true? Y minus x is equal to phi of, how I have defined? This is mod x into y minus x tilde. Since phi is a fundamental solution, the fundamental solution, and these are the, and it is radial. That means we need to check whether mod x y minus x tilde is equal to mod of x minus y, whether or not true. Then this will imply this, and this will imply phi x equal to this, provided y is in del b. Okay, now let us check. Mod x y minus x tilde square. This is mod x square y minus x tilde square. So now mod x, that means mod x square minus, and what is x tilde? X by mod x square. 2 into x dot y by mod x square plus 1 by mod x square. Okay, we know that mod y is in the boundary. We have to use this fact, right? That means mod y equal to 1. That means mod x square 1 plus minus 2 into x dot y by mod x square plus 1 by mod x square. Multiply. This is mod x square minus 2x dot y plus 1. This is nothing but x minus y whole square. See, if y is in the boundary. So if if y is in del b01, then mod x is equal to, this imply phi of x minus y is equal to phi of mod x y minus x. Clear? Is that clear? What happened? Is that clear?
Yes, sir.
All of you? Is that clear, all of you? Is that clear, all of you? Sanjeev, Yash, Kritika, Vivekanand, Ekansh, Vishwa,
So,
Shammi.
Yes,
yes,
sir.
sir.
Okay, good. So that's all. So, okay. Now we will see that. So there you know now, therefore you can compute explicitly the green function. Therefore, the green function, the Green's function, sorry, the Green's function is given by g of xy is given by phi of y minus x minus phi of mod x y minus x tilde. Okay, therefore the Green's function is given by this, because this is your phi of xy. Okay, now again we want to compute the, what is del g by del e. If you compute, you will see that this is nothing but minus mod x square by, for n equal greater than equal to 3. Of course, at n greater than equal to 3. Clear? Okay. Now whatever we have done is, this is for B01. Now remark, we would like to see what will be happen for B for any radius r. So any idea what we should do? Any idea? So we have computed the Green's function for B01. Now I would like to compute the Green's function and to solve the PDE for B0R. Instead of 1, I have R now. What I will do?
We can
Hmm?
do it by
Uh-huh.
in under 5.
Again,
We can take mod x by r.
kind of. That means we have to do the scaling, right? Now suppose the question is U is in C2B intersection C B closure. Okay, solves this solves Laplacian u equal to 0 in, this is your B01. This is B01. Okay, this B is B01. So I just write down the Poincare kernel. Okay, u equal to G. Then ux is given by this is a Poincare kernel. You know this. Why, how I get it? Because del G by d, I just computed the del G by d. Okay. Again, the converse is also true. You can check. Converse is also true. That if u is a solution of this, then u solves. If you define u to be this function, then you solve this PDE. Okay. The converse is also true. You can use the book of Evans. If you don't, I will again explain it. You can see the book of Evans. Okay. Now I would like to do it. Now the question is, now I have to write for B0R. Okay. Okay. That means suppose V I am writing to C to B0R solves the PDE. V equal to 0 in and V equal to G. Now what we want to, as Yash mentioned, we have to define some function Wx as V of Rx. X in B0. Okay, then V is defined on B0R. So X is in B01. So R of X will be R of X is in B0R. So the domain is well defined. Okay, then clearly Laplacian W of X at some point X is equal to Laplacian of V at the point Rx. So Rx is equal to 0. For any point in B0R, Laplacian V is 0. So that is equal to 0. Okay. So what is the boundary condition V satisfies? So W of X is equal to V of Rx is equal to G of Rx, because at the boundary V is given to be G of G Rx when mod X equal to 1. Okay. Therefore, you write down the points because W, now you have a function, therefore we have some W which satisfy W equal to 0 in B01, just scaling, nothing else, and W equal to G of Rx in del B01. Okay. Okay. Now you just write down, therefore using our previous one, we can write down that if W is a solution, then W will be written as 1 minus mod X square by n into alpha n del B01 G of Ry, because it is given Rx by x minus y whole to the power n d sigma y. Okay, is that okay? Now what I will do? Any idea? This is a problematic, no? R of y, it looks not nice. You will put Ry equal to z. So d sigma z will be r to the power n minus 1 d sigma y. Okay? So d sigma y is d sigma z. Okay? So and the ball will be now B0. Y is Z by R. If we compute this, we will have is equal to 1 minus mod x square into R by n into alpha n del B so R dgz by Rx minus Z d of sigma z. This is Wx. Now what I will do? We are almost there. Now what I will do? What I will do? Huh? We are done, right? What I have to do now? We want to write back everything in V. What I have to do? Because this is in W. Now I have to write that everything is in V. What I have to do? Yes? Just define a capital R. X is Rx. Because this is your A. This one. then your x is in, this capital X is in, this capital X is in B del B0R. So we can write as square. This x is capital X by capital X by R square. If you write down, you will get it like this: n alpha n R del B0R x minus z d sigma z. So this is the Moeso kernel for R, for any R. So this I can write as del B0R kxz dz d sigma z capital A. Is that okay? Just I did the scaling, nothing else. Change your variable. Is that okay, all of you? Atharva, Yash, Sanjeev,
Yes.
Kritika, Vivekanand,
Yes, sir.
Ekans, Vishwa, Shami. Is that clear? Huh?
Yes,
Is
sir.
that clear? Okay. Now final topic which I will do now. Of course, this K is called the Poinsot kernel. You know what is called. This is called the Poinsot kernel. Poinsot kernel for B0R. Or the Poinsot formula. Okay. Okay. Finally, we will do something very interesting. We want to solve this PD. Okay. Something called, this is the last topic. Energy or a variational method. So tell me something. I ask something. All of you know when a function attains maxima or a minima? Atharva, Yash, tell me some function when the function, some property of function when it will attain maxima or minima. Hmm? Hmm?
Like it's continuous in a compact domain.
Excellent, excellent. When a function is continuous on a compact set, then we know that the function is a bounded and maximum and minimum is attained. Yes or no? Yes or no? Yes or no?
Yes, sir.
Yes, sir.
Okay. So what is the Rolle's theorem? Can anyone state? Yash, Kritika. What is the Rolle's theorem? Hmm? एटलीस्ट रोल्स थ्योरम बता दो क्या है एकांश व्हाट इज द रोल्स थ्योरम
Sir, if a function is continuous on closed AB and differentiable on open AB, so that f is equal to fb. Then f dash x, the function of x is equal to 0 with the x lies between closed AB.
okay 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 so that is also something no so if you draw the picture so just roughly I'm drawing okay let's say A to B this is your FA this is your FB something like that right there is a point if function is continuous some C where it is right it might at least one it might have like this also or like this also like that also, right yes or no yes or no that means
Yes.
there are some local maxima or minima kind of thing yes or no So also it is not all, this is not always true, but it is also true if the function have a maxima or minima at an interior point, then you know that f prime of x is equal to 0 at that point, kind of thing. So somehow, of course, f prime of x equal to 0 not always guarantee that there is a maxima or minima. Yes. Example, can you tell me an immediate example?
Constant function.
Another constant function is x cube. No, not x cube. Yeah, x cube. This function. Right? Yes or no? At the point 0, sorry. Yes or no? 0 at the point f prime of x is 3x square. So f prime x equal to 0 at x equal to 0. Is that a function has a maximum minima at 0? Yes or no? Maximum minima है इस point में at x equal to 0? Yes or no?
No, sir.
Why? You don't know these things, saddle point and all those things? Huh? Yes, you don't know? Yes or no? Tell me. Nothing is. You know, na, f prime of x, if it has a maxima or minima, then f prime, if it's an interior point, then f prime of x equal to 0. But the converse is not always true. So if f prime of x equal to 0, this does not always guarantee that it will have a maxima or minima, right? Am I correct?
Yes.
Sanjeev, Vivekanand, Ekansh, Vishwas, Shammi, Kritika, Atharva. Am I correct?
Yes, sir.
Yes, sir.
Okay, good. So somehow the characterization is, suppose you have a maxima or minima, somehow the characterization is roughly is f prime of x equal to 0 if it has a maxima or minima. Now we will see that solving a PDE is equivalent to find some function from some space x to r. Of course, this space is not a, b or something, such that j prime of x equal to 0. This is an if and only if. Of course, this is a very deep topic. This is called variational methods, or a calculus of variation. It is called. This means that to solve some PDE, it is enough to construct the critical points. In some point f prime of x equal to 0, we call it the critical points of the functionals, right? What are the definition of critical points of the functional f is in C2 is that if all those points for which f prime of x equal to 0. We would like to collect all those critical points, okay? You'll see, I will give you a not an abstract way and a very particular example, okay? So somehow it is related, solving a PDE is somehow related to finding a critical point of some functional, okay? This I will do here. This is of course a very deep topic, but you will see. Before that, just a small theorem you know already, minus Laplacian of u equal to f, u equal to g in omega on del omega. You know that, where omega is a bounded domain. With smooth boundary. Has at most, I have told this, has at most one solution. The proof, just write down the proof. Suppose it has two solutions, u1 and u2. Suppose. Then you define u to be u1 minus u2. Then minus Laplacian of u equal to 0, u equal to g. 0 in omega on del omega. I just want to derive, no, by maximum principle you already know, na? By maximum principle. By maximum principle, you know. I did this already. Principle u equal to 0, these imply u1 equal to u2. But let us do it in some other way. So what we have? Minus Laplacian of u equal to 0 in omega and u equal to 0 on del omega. Minus Laplacian of u equal to 0 in omega means I can integrate. Right? Yes or no? In omega dx. This is again 0. Sorry, 0. Now you multiply this equation into above equation by u. That means minus Laplacian of u dot u equal to 0. In this equation I multiply with u. Okay. That means minus Laplacian u is 0, so minus Laplacian. I use the integration by parts here. Gradient of u mod square minus del omega. Del omega u equal to 0. So this part will be 0 equal to 0. What we obtained? Gradient of u square equal to 0. What can I say about u? What can I say about u?
Constant.
Exactly. These imply u equal to constant. Of course, omega is a connected, all those things are there. Constant. U is a continuous function, u is a constant in omega, and also know that u equal to 0 on del omega. So what will be the value of the constant?
0.
So u equal to 0. So you just see what I have done. This equation is given. I multiply this equation with u and integrate by part. And what I did, I did the integration by parts. Okay. I multiply by u, so it is 0. So minus Laplacian of u into u equal to 0. So gradient of u square equal to 0. So gradient of u square is equal to 0. This is one method what I have done. Now I will do a very nice theorem. This is called Dirichlet principle. It's called Dirichlet principle. That is a minimizer. Okay. Dirichlet principle. Is that minus Laplacian u equal to f in omega, u equal to g on del omega, can be characterized. The solution of the above problem, the solution of the problem P can be characterized as the minimizer. We'll see. I will see. Write down everything. Write down of an energy function. What is the meaning? I will tell you. Don't worry. What is that? Is the following. Define a space. No function space you define. U is in C2 omega intersection C omega closure, and u equal to g on del omega. Okay, I define a space X. U is in C2 omega such that u equal to g on del omega. I define a space and a function from X to R by j of u is half gradient of u square minus integral f u. That means so everything is well defined because u is in C2 function, so gradient of u is a, you know, everything, omega is a bounded domain, so everything is justified. So j is a function from X to R. Clear? Now what is your x? X, you know about some function analysis. So x is nothing but a space of continuous function C2 intersection C omega closure function such that u equal to takes the value g on del omega. Is that okay? So this is a function space. Yes or no? Yes or no?
Yes, sir.
Okay. So this I have defined a function like half gradient of. You will see what is this function. So j is a some function. Is that a continuous function? Is j is continuous? Yes or no? What happened? Is J continuous?
Yes.
Yes. But here unit ball is not compact because this is a infinite dimensional vector space, right? So here if you take a compact like a ball mod x equal to 1, norm of u equal to 1, you know unit ball is not compact, so you cannot conclude all those type of things. Okay, so this is a, you can easily check that u is a continuous function. In fact, it is a C1 function. You don't have to bother about it. So I define a function from x to r. Okay, now what I state in this theorem is the following. We said that u is C2 omega. This is very beautiful theorem. Is a solution. U, a function, is a solution of the equation Laplacian of u equal to f in omega and u equal to g on del omega. If and only if, a very big statement, if and only if j of u is the minimum. You know what is j of v? This is j. This is u. The j is defined on x. So this says that minimum of j of v, v belongs to x. If it is some u, j of u, if the minimum is attained, if the minimum is attained by some function, if the minimum is attained by some function u, then you solve this PDE. And vice conversely also true. If you solve this PDE, then this function j will attain the minimum at the point u. Is that clear? Is that clear?
Yes, sir.
Yes.
So if j of u, if the minimum is attained by u, then u is the solution of this PDE. See, now you have completely suppose this theorem is true, then you forget about the solution, how to solve all Green's function method, everything you forget it. Just you have to you write down the functional and try to find the critical points, whether it has a minimum or maximum. So what I do in my research is the following. So this, of course, this is quite difficult. So I define some functional on some vector on some space and because these spaces are infinite dimension, this is not always true that it will have a minima or a maxima. So that is why we need to understand the topology of this vector space. So PD is something related to sometime studying PD is something related to very similar to something algebraic topology. So whether you have a homology, cohomology, everything is used in prove this type of theorem. Okay. Of course, here I said that j of u is the minimum. Minimum is already attained. I have written down. But the question is the difficult. When suppose you solve some kind of PD, when the functional will attain a minimum. The big question what we study in the PD is when the functional j will not this type of functional, but I am saying that such functional. This is a very easy functional. When the j will attain minimum, critical points, maxima or minima. This is a very deep problem, maxima or minima. You understand? The idea is to nowadays, this is called a modern theory of PDE. Nowadays, to study some PDE is equivalent to study some maxima minima, some maxima minima, some maxima minima for the functional j. Is that clear? Is that clear? When j will attain the maxima or minima. Suppose you know that when it will, so here the theorem is easy because I have said that if it attains minima at u, then u is a solution. But the question is something different. Question is when j will attain maxima or minima. That means now the problem is forget about the PDE. This is a new problem. The problem is there is some functional which is in an infinite dimensional vector space. Okay, this is not easy. So x is now always the function space. So there are some kind of functional in this type of topology argument. So topology, why we are studying topology? Topology sometimes as I said, why I am doing Rolle's theorem. Rolle's theorem is nothing but some topological property. If you don't know, I will explain one day. So how the topology properties are confined in the Rolle. This is a very basic theorem, the Rolle's theorem. What we study f prime of x equal to 0, right? But no, actually there is something more. In Rolle's theorem, there is something more. Just I give you some brief explanation. What is Rolle's theorem? B. This is FA equal to FB, and this is some point C. Okay? C and F prime of C equal to 0. Okay. You consider a set J of let's say C1. This is a set of all x in AB such that f of x is less than equal to C1. Okay? Now you consider this C1. Here C. C1. Okay, this is your C1. So what is JC1? Anyone? For this C1? Huh? Huh? What is the set JC1? If I choose C1 to be like here.
All of AB.
All of AB. Very good. Now let us take this C1. Or C2. What is JC2? Huh? What is JC2? Let's say A1, B1. So what is JC2? Please. Is a set, the function which is below this set. What is that set? Yes or no? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Huh. So what is the difference between these two sets? Topologically?
JC2 is not connected.
Excellent. This is connected, not connected. Okay. So Rolle's theorem actually gives whenever there is a critical point of function, there is always a change in topology. How beautiful this theorem you see. Whenever there is a critical point of a function, if you take just above the critical point, below the critical point, there is a change in topology. Okay? You understand? You understand? Did you understand? Because see C1 and C2. C1 is above this. If you just take this, if you take this is FC, so you just take FC plus epsilon. So this is your C1, and you take FC minus epsilon. This is your C2. Now if you take JC1 and JC2, there is a change in topology if at the point C there is a critical point. Not always, but roughly this is always true. Of course, in a compact set it is always true. But if there is R, this is not always true. You understand? Did you understand? If there is always a so you don't know a priori that whether there is a critical point or not. So what we will study? Studying a PDE means you want to find the critical point for the functional. Now that means you want to study the functional, the topology of this functional C1, JC1 and JC2. You understand? If there is a change in topology at some point, then we always say that there might be possible that there is of course this is not that easy, there is a critical point. And once there is a critical points or maximum in this type of critical point means f prime of C equal to 0. Once there is a critical point, we solve the PDE. Now understand? So now the solving a PDE means study of topology of JC type. These are known as some you don't have to understand, they are called level sets. So this one dimension you can compute with connected, this not connected. But when you are in a higher dimension or in some infinite dimension or some you have to study, because connectedness is very easy to see in the here in this interval and all those things. But once we are going in a higher dimension, means in R2 or 3 or 4 or n, sometimes maybe connect, then it is easy to compute whether if there is a change in topology, means the homology, we want to calculate the homology group of JC or a fundamental group of JC, or what is the fundamental group of JC2. If there is a change in the fundamental group, then we call it there. Of course, that means there is a change in topology. That means there is a critical point. Okay, you understand? This is just I give you a glimpse of the actually what is the modern PDE theory. Okay. So it is sometime people call studying PD is means sometime it is studying some topology. Okay, is that clear, Atharva? This is just
Yes, sir.
just give you some hint. See, just a Rolle's theorem. You haven't studied in this way. You haven't looked the Rolle's theorem, right? There is a change in topology, right? Okay. Now we will solve this. So forget it. If you don't like it, forget it. So, but now this theorem we have to prove it, right? So if U is a solution to this PD, if and only if J is the minimum. Okay. Okay. Good. Proof. Proof is not very difficult. Suppose J attains minimum at U. Okay. Then we claim that U satisfies the PDE. Fix some cis infinity function. Okay. And define a function so you know that it is given that a priori it is given that U attains its minimum at U. Okay, J attains its minimum at U. So I define a function f of t is nothing but J of U plus t phi. So U is known because you know that it attains at the point U. Phi is you fix some function phi. Okay, and t is the parameter. So this is so if I write on f of t, this is a function of one variable. Yes or no? So f is a function from R to R. Yes or no? What happened? Yes or no?
Yes, sir.
So where is the so we know that J attains its minimum at U. So what will then at what point the f will attain its minimum? If a attain will 0 exactly by the hypothesis this hypothesis that suppose J will attain because at t equal to 0 J of U which is the minimum by the hypothesis f has a minimum t equal to 0. Okay, so f prime at t equal to 0. F is a kernel for t equal to 0 at t equal to 0, which is equivalent to say that ddt of t equal to 0 J of U plus t phi equal to 0. Now let us compute what is J of t phi. Okay, what is then we will see that what is the meaning of ddt of t equal to 0. Okay, let us compute J of U t phi. Okay, what is this? Half gradient of U plus t. If you expand it, you will have this half this is your J of U plus t phi. Now you tell me this is J of U plus t phi. Now you tell me what will be ddt at time t equal to 0 J of U plus t phi. Just differentiate with respect to time. What will happen? First term क्या होगा? Differentiation with respect to t. What will happen? Anything t is there?
0.
0.
Next term this will happen t. So gradient of U, gradient of phi. ये t square है 2t. 2 cancel only t is there but t equal to 0. This is also 0. If this is also 0, this will come. ठीक है? Is that okay? Now I said that this is f prime of t. at t equal to 0. Because u attains as minimum, that means equal to 0. That means this is equal to 0. That is I got it. Gradient of u, gradient of phi minus f of phi equal to 0. Now what I will do? Phi is a compact supported function. What I will do now? क्या करूंगा अभी? Always use integration by parts. Minus Laplacian u is the boundary. What will be the boundary term? Huh? What will be the boundary term? Plus del omega del u by del nu phi d sigma. So what is the boundary of what is the value of phi at the boundary? Phi is a compactly supported function. Huh?
0.
0.
So this term will not be there. This is now omega Laplacian u minus f phi equal to 0. This is nothing but Laplacian plus f. This imply omega Laplacian u plus f into phi equal to 0 for any phi is in cc infinity of omega. So क्या होगा इसका आंसर? Then this imply because phi is an arbitrary. So for any phi Laplace cc infinity Laplacian u plus f equal to 0. I have done this. F equal to 0 for all f. If f is a continuous function, then all f cc infinity. This is a major theory. F equal to 0. Yes or no? Exercise. I have done this. I have told you how to do this. Okay? So that means this imply f equal to 0. That means minus Laplacian. ठीक है? Is that okay? Is that okay?
Yes, sir.
Okay, and I've defined the space as all C2 such that u equal to g. So on the space I have defining, right? So u equal to g on the boundary. So one way is done. Now the next way, conversely. Suppose u solves star. We want to show that j of u is the minimum of v belongs to x jv. That is, we have to show that j of u is less than j of v for any v in x, and of course u is also in x. So u solves the PD. So we have minus Laplacian u equal to f. So minus Laplacian of u into v minus u. V is any, you take v to be any point in the set x. X means the function space, okay? And you multiply with f into v minus u. Okay, you multiply the equation, you multiply this equation with v minus u. You are given u to be a solution, you are known that u is a solution, so it's not problem. You can choose v to be any element from this set x. Clear? So I take v minus v is a well defined. This is also a function in x. So this no, not in x, some function. You multiply with this equation Laplace minus Laplacian equal to f, and then integration. Okay. Again, what I will do, integration by parts. Okay. Gradient v minus. So what will be the boundary term? What is the boundary term?
0.
Why?
So v equal to u on del omega?
No, it is 0 because I have taken x. What is the space x? X is the space all v is in C2 omega dot 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 such that v equal to g. And also it solves the PDE means u equal to g on the boundary, v equal to g on the boundary. So both are 0, right? So v equal to u equal to g, right? On the boundary, right?
Yes, sir.
So integration fv minus integration fu. So this is gradient u square minus gradient of u into gradient of v equal to integration fv minus integration fu. You just rearrange it, you will get that omega gradient of u square minus omega f of u. This is equal to gradient of u into gradient of v minus fv. Okay? Here you use Cauchy-Schwarz. Okay, this is or Helder inequality minus fb. Now you use this thing. 2 into ab is less than a square plus b square. Okay, you use here. So what we have now, gradient of u square minus f of u, that I have now is less than gradient of u square half gradient of v square half minus f into v. Right, now you use 2 into ab. This is your a, this is your b. 2 into ab, so this is 2. This is less than half into square plus half. इसको हम इधर ले जाते हैं इस साइड, that is half gradient of u square minus f of u is less than half gradient of v square minus f. So this is your j of u is less than equal to j of v. Okay, since v is arbitrary, we have minimum of solved. Okay, is that clear?
Yes, sir.
Okay, yes, clear. See, you have to understand the integration by parts. That's the only thing. Okay, this is the only thing, that you have to understand integration by parts properly. What I am using is the integration by parts. Okay, is that okay? Yes, Sanjeev, Ekansh, Vishwa, Shammi.
Yes, sir.
Yes.
Yes, sir.
Okay, Navneet.
Yes, sir.
Kritika.
Yes, sir.
Shammi.
Yes, sir.
Okay, so this is the end of the. Also, I in my notes there is one example to solve. So last time he was someone asking me some example of example. In my notes, he will find one example which I am not going to do. You just have a look. One example of solving a Dirichlet problem, just like a square, a rectangle. I want to solve uxx plus uyy equal to 0. How to solve that particular PD in a rectangle. Okay, that is there in the, as an example. Now, I am not doing that. You just have a look on the in my notes when I will upload the notes. Okay, that's all. So this is the end of the Laplace equation. Next I will do heat equation. Okay, so it will take 3 class for a heat equation and 3 or 4 class, 4 class and 1 or 2 for wave equation. So I will tell you the syllabus for the end semester. Okay, so Thursday is the exam. So do you have a class on Friday evening? Or otherwise I will want to take this makeup class on Thursday. Thursday's class I will take it on Friday. So whoever comes, or I will just. So do you have a class on Friday in the evening? Anytime you are free?
Sir, actually we have tutorial classes in the evening on Friday.
Okay, maybe I can use that tutorial class to start take this class. Maybe. So already done. All the Laplace problem are done in the tutor in tut.
So only one is left, like fifth one.
Fifth one. So maybe she will the both of them will do in the next class. Maybe what I will do, I will take the tutorial class and half an hour more to end that to make up the class on Thursday. Is that clear? Yes, Sanjeev, Ekansh, is that clear?
Yes, sir.
Yes, sir.
Okay. So if you want to come. Otherwise, I will record it. I will post it. So I will start on that day the heat equation. Okay, because I am missing this Thursday class, so I don't want to miss those classes. So let's make it on Friday. Is that okay? Okay.
Yes, sir.
Yes.
Okay. Let's so do well in the exam. So
Sir,
ah.
so one thing, sir, you are